Okay, so what are the questions for me? Because we got you here and Shauna's on Discord. You guys got any questions for me?
I'll see if she has any questions first.
Okay. Yeah, did you have any specific questions, Shauna?
I don't have anything specifically. I'm just here for like general stuff, but I think my like least comfortable subject is Verilog. So I don't know if everybody else like has any questions, but
I'm sure
that would be
most
what I would
everyone would
cover.
want to go over Verilog stuff, so we can definitely do that. What's this? Okay, let's see. Someone else hopped in the Discord. Did you have any specific questions, or just coming in for general stuff?
Just for general stuff.
Okay.
We'll see out along the way.
All right. So let me go ahead and open up Visual Studio Code. That way I can share my screen and type some stuff up. There we go. New file. Let's do 1-25-23. Desktop. That. Okay. All right. My computer's lagging very hard, so I just got it to open. I'm going to go ahead and show you guys my screen. There we go. Should we get right? Okay, cool. Can everyone see my screen?
Yes.
Okay, cool. So every module you make in Verilog is always going to start with module, end with end module, and then the next few things that go here, firstly, is the parameter list. You guys won't really deal with that much. You just won't really talk about it, but I'll leave it there for a second. And then most importantly, the thing you should be concerned with here is the port list. So the port list is going to contain all of the inputs and the outputs for your module. Just like if you were drawing a black box diagram, all the things coming in and coming out of that black box diagram better be in this port list. So for example, you might need a clock signal. So whenever I say I want an input signal, I say input logic. And then let's do clock. And then maybe I have another input signal, say reset. Oh, the highlighting of this is very bad. Okay, well, whatever. And then you have, say you want some outputs, so you have to say output logic. And maybe they are multi-bit signals. Could do something like 3 to 0, out 1. and that would be just a generic port list. If you have multiple signals, even if they're all outputs or all inputs, it's important that the bit widths correspond to what you want them to be. So if we have one output that's 4 bits wide and another output that's, say, 2, we're going to need to specify that on another line here. So I'll say output logic 1 to 0, out 2. This is how it should be highlighting for the rest of that stuff, but it is not for some reason. Whatever. Maybe it's because of this. That's why. Yep. Okay, cool. And don't forget that in this space that I haven't written here, what goes there?
Your module name.
Yeah, the name of this particular module. So we can call it whatever we want. Say my module. And as mentioned before, you can put your list of parameters here. It doesn't matter. For this class, you're probably not going to use it too much, so I won't. And I think actually, it'll go here. Sorry, I had it in the wrong spot. It'll go after that name there.
Can you elaborate again why we have 2 outputs? Is that to match the number of inputs that we want?
It's just whatever your system needs. It doesn't matter why. This is just an example. It's just showing you how to write syntactically what you're trying to write. It just depends on what your actual circuit needs. If your circuit needs a 4-bit output and then a 2-bit output, there you go. If your circuit doesn't need a 2-bit output, then now you're done. So it just depends on what you need. We could also have more inputs. You know, we could have an input logic as, say, A, B, C, all of which are 1-bit signals. And you guys probably won't talk about it also, but you could also have input and output simultaneously. That's called bidirectional. It just means that you can receive information from that and also output information to that pin. You won't talk about that too much in class, but if you want that, this is how you do it, in-out logic, and then you put however many signals you want. So that's general port list stuff. Again, don't really worry about the parameter list. You're not going to use it.
Yeah, I haven't seen that too much.
Yeah, you might. I think Dr. Harris has a few examples of parameterized modules, and there's nothing wrong with doing parameterization. It's just you just probably won't talk about it that much. It's just not a huge deal. Okay, so any questions about what we currently have here, about the port list stuff? Okay, any specific questions for me? Or should I just continue with general system Verilog stuff?
Can I make a request?
Yeah, go for it.
Can we add in some structural module
Yeah, let's do some
stuff in
structural
here?
stuff. So, when you're asked to make structural things, what does that mean?
It's like making components, like gates, and then adding them into a bigger picture.
Exactly, yeah. So you make small pieces, and then you take each of those small pieces, instantiate them in another module, and you just wire them together. So let's do, say, an example circuit that we can do structurally. So I'll go ahead and draw something up on the board, and I'll then code that up in Verilog structurally. So let's say each of these blocks I've listed, do you guys know what these are? These blocks?
Are those muxes?
Exactly correct. Those are multiplexers or muxes. And what have I made? That's a little bit of a harder question. What have I made here?
A 4 mux, right? Like,
Yeah, a 4-to-1 multiplexer. So you'll notice that each of these smaller ones is what we would call a 2-to-1 multiplexer. So it has two inputs, A and B, and then one output Y. So it chooses between two inputs and outputs one of them. Whereas here, what we do, if we were to say, look at just a black box diagram, we have 1, 2, 3, 4 inputs, 2 select lines, and a single output Y. And so we've just made a 4-to-1 multiplexer from a bunch of 2-to-1 multiplexers. This would be a structural design. If you actually saw me putting all the gates in these and then arranging the gates nice, that would be behavioral. We're describing what the gate level behavior looks like. So I'm going to go ahead and code this up. And the way we're going to do it is we're first going to create the code for a single multiplexer, and then we're going to instantiate 3 of them in a new module for the 4-to-1 multiplexer. So we'll go ahead and type that up. All right. Okay, so I'll go ahead and make my new module here. So I'm going to call this mux 2-to-1 because it's going to be a 2-to-1 multiplexer. And I'm not going to parameterize it, though I can later if you guys want me to. Just let me know. I'm going to say input logic. And what are the inputs for a 2-to-1 multiplexer?
a select input and 2 other inputs.
Yeah, so I'll call them A and B for the 2 generic inputs that are coming in at these terminals. And then I have another input, the select line here at the top, determining whether or not we output A or B. So I'll call that select. And then I also have my output logic. And I'll call that one Y. Okay. You'll notice that I haven't specified bit widths for these. Again, like I have mentioned in previous office hours, if it's a single bit signal, you could, if you wanted to, specify it like this. You don't need to, though. It's just unnecessary. So I'll leave them like this. And now we have to write the behavioral module, i.e. gate level or like case statement, to describe how the multiplexer works. So what am I going to write? How do I make a multiplexer? We can go ahead and try a case statement, yeah. So what do I type up for that if I want to do a case statement? Yeah, very good. You have to put that in an always com block. You don't need the begin and end here, but I'll leave it just because it auto-filled it for me. And then within the always com block, I need to put case. And you could put case Z if you want to do, if you want to use don't cares. For the moment, though, I'll leave it as is. So I'll leave case. And the case is going to depend on what?
On S.
I think select's a pretty reasonable thing for it to depend on. Whenever you have a case statement, it has to be ended with an end case. Not end, but end case. It's a little weird. Now in here, I do each of my case blocks kind of like if I was writing a case block in, or a switch statement in C++. So kind of similar to that. So what I would do here is I would say, well, the case where we have select is 0, or the case where we have select is 1. I could have, if I wanted to, written just 0 and just 1, but I'm writing this as follows to specify that select is a single bit, is a 1-bit signal. And so when select is 0, what do I want y to be? So when select is 0, which input of the multiplexer do I feed to the output? We feed A, yeah, that's our 0 here in this diagram. And then if I selected select as 1, then y would instead be what? It would be B, that's right. And so now we're pretty much done. All we did here was we had an always-com block, and we said, well, if select is off, then y is going to be A. Otherwise, when select is on, y is going to be B. And just as kind of like a sanity check, we can also do a default value here. And I recommend doing a default value for all of your case blocks, just in case you have some sort of unknown value. Say you received don't cares, or X's rather, undefined values. You want some sort of basic state to be in. And so you can choose whatever you want to put here. Say I'll do B. Or actually I'll do A. By default, y is going to be A. But if you're in the case where select is 0, y should be A. If you're in the case where select is 1, y should be B. And if neither of those happen, if something goes wrong, we can always fall to this default statement. So normally you'd have that. You don't, like I mentioned earlier, actually need this end or this begin. The reason why is because this case end case counts as one long complex statement, and so you don't need to tell the parser that, hey, this is all within the always-com block. It knows it is. If you then had some extra stuff down here outside of the case block, you'd need a begin end. But I'll leave it anyways. Okay, that's one way to do this. Another way to do this, I'll put in comments, is with an assign statement. And we could actually do this using, if we knew, the gate level logic. And we actually do know the gate level logic. I can go ahead and possibly draw that up with my marker. So it might be a little hard to see on the camera, so let me open that up. And essentially all that's happening here is, I know that's kind of hard to see, but you have two AND gates. So if S is off, then what's going to happen is this input of the AND gate is going to be on, and this input of the AND gate for B is going to be off. So this is going to contribute at 0, and A is going to be fed through to Y. A is going to go through this AND gate. If A is 0, this output's going to be 0. If A is 1, this output's going to be 1, and same thing for the OR gate. You could derive that from a truth table if you guys want me to, but this is the schematic, the gate level schematic for a multiplexer, and we could code it up just like this. And so the code would be as follows. So I'm going to assign y equal to not S and A, or not select and A, or select and B. Order of operations says that ands are done before ors, so I don't actually have to put, say, parentheses around these terms to specify that the and takes precedence. It already knows that, so I don't have to put the parentheses like this. And this here would accomplish the exact same thing as this always come up above. Makes no difference which one you go with, they are identical. The only difference is what makes more sense to you. Okay, so any questions about the two different ways to do this behaviorally? Okay. So now that we've made our MUX module, our MUX 2-to-1, I'm going to make my structural mux 4 to 1 module. So I'll do that like this, module mux 4 to 1, and I'll say input logic. And remember, for our 4 to 1 mux, we have a bunch of inputs. We have A through D, so A, B, C, and D. And for my 4 to 1 mux, I have actually 2 select line bits. So I'll do it like this, input logic 1:0, select, because I have 2 bits for it. And then I'll say output logic, and I'll call this one Y. I'll do a little formatting here. Okay. All right, so everyone all right with this port list? We have our 4 signals coming in. That's why it's a 4 to 1 mux, and we have our 1 signal coming out. And then we have 2 select lines, one for the first column of multiplexers and one for the second column of multiplexers. So any questions on that? Okay. So now I'm going to go ahead and make the exact hardware that I have up on the board, which is 3 multiplexers. So I'm going to instantiate those. So the way to instantiate a module is you say mux 4 to 1, which is just the name of the module, and then you're going to say this specific instance of that module. What do I want to call it? And I'll call this mux 1, just to give it a name. And mux 1, I'll call this top left guy. So that top left one has A and B as an input, and S1 as an input as well. So A, B, and then S bit. Yeah, I'll go with S bit 1. And then I have my output, which is just a wire. This wire is not an external signal. It doesn't go out of this block. It's actually an internal one. And because it's an internal signal that's not in the port list, we have to specify this signal. So say something like logic N1 for node 1. One small nuance of System Verilog when you put it into a compiler is that if you actually don't specify this, and you were to just put N1 like that, and if you didn't have this name here, it would actually work. The reason why is because if you have a signal, it's going to just make a 1-bit signal for you that has that name. Here's the problem with that. What if the signal you were trying to make was actually a 2-bit signal, but it just made a 1-bit signal there, and the port list is all messed up? This is an issue. And so a lot of the times compilers like ModelSim are going to just make that nice little signal for you and be like, it's okay, I fixed your problem for you. Here's your signal. And it's actually all ruined and you have no idea why. And it's just because you didn't declare the signal. Like I said, here it doesn't matter because it's a 1-bit signal. However, just in general terms, always declare your signals whenever you're going to use them. So here I have N1. And indeed, I'm going to preemptively make an N2 because I know I'm going to need one later. So again, this N1 is just the name of the wire after that first multiplexer, and N2 is going to be that bottom wire. No luck with it. Okay, so I'll go ahead and make that second mux right now. So mux, oh, I made a mistake. Anyone catch it?
Well, I actually have a quick question on the select bits.
Yep.
Why is it a 2-bit if it's just either 0 or 1?
Why is it 2 bits if it's 0 or 1? Like this, you mean?
Yeah.
So that 1:0 specifies basically the names of each of the bits. So you have bit 0 and bit 1, which is 2 bits. You could have it named 2 to 1 or 2 to 0, which would imply 3 bits because you have bit 0, you have bit 1, and then you have bit 2, and that's 3 bits in total.
Isn't select only 1 bit though?
Great question. For a 2 to 1 mux, absolutely. But for a 4 to 1 mux, you need one select line to tell which of these two multiplexers to choose between A, B, or C, D, and then you need a separate bit for this guy.
I see. Yeah. Okay, that makes sense. Thank you.
Yep. So anyone catch my mistakes? There are two. Two mistakes. No, you're good. I'll show you my first mistake. This is supposed to say 2 to 1 because the module I'm instantiating is this guy up here. Yes, that's the first mistake. Yeah, no, ask questions. Ask questions if you guys don't understand it. Second mistake. Oh, yeah, go. Second mistake is this. That should be named select instead of S. Okay, so what was your question?
I have a question. For the N1, you know how you said you don't need to declare it?
Yep.
You could just add it.
Yep.
Let's say you were to add like the bits, specify the bits in N1. You could put like 2,
You mean like this?
yeah, but like inside the, like here.
Oh, in here?
Yeah.
Oh, well, if you wanted to specify the bits of N1, N1 would have to be a multi-bit signal. So I could actually do this if I wanted to, yeah. And if I made N1 2 bits, so I could do something like this. I think I get what you're saying. So instead of having N1 and 2, I can name it the signal N, and then bit 1, bit 2, or bit 1, bit 0, and I could do this. That would work, yeah. That's just saying use the bottom bit of N for this multiplexer output. And then for my next multiplexer, I could do N bit 1. That would totally work, yeah.
Does the compiler just error out if you left it as mux 421?
If I left it like this,
Yeah.
it would yell at you for like recursive module definitions because you have this one's 4 to 1, and then you're trying to instantiate it within itself, and so it's a recursive module. And you can do that with recursive functions, but you can't do that in hardware. You don't have a recursive module. It doesn't make sense. So it'd probably yell at you for that. But yeah, you could do this. Or, like I mentioned, you could name N1 and 2 and put them as separate ones. But this works too, absolutely. Okay, so now I'm going to make that last multiplexer. So I made my first two. And I just need to change this second one to have C and D as the inputs. So I have my first multiplexer. And actually, this one needs to be one as well. So I have my first multiplexer, which takes in A, B, and select line 1, and outputs N1. And then if I have my second multiplexer, which takes in C, D, and also select line 1, and outputs N0. And now I need to make one last multiplexer, so I'll do the same thing again. And this multiplexer takes in the outputs of the previous two. So I'll do N1, N2, or N0. So that's the outputs of the two previous multiplexers. And then it actually uses select bit 0, and then it outputs to Y in our diagram. And so I would label that Y. And so what we've just done is a hierarchical or structural definition of this module. I could have gone down to the gate level and figured out what all my AND gates, my OR gates, my NOT gates were, and wrote that code here. Or you can use other modules and make it from those. And that's what we just did. Typically, structural modules consists of almost entirely these kinds of instantiations, and also, your signal declarations, and maybe like 1 or 2 assignment statements. For pretty much any of your structural modules, that's what it's going to look like. Okay. So, any questions with this structural module?
So behavior would have been the mux 21? Or my
Yeah, MUX 2 to 1 is behavioral, absolutely. And I can show you MUX 4 to 1 as a behavioral module as well. So let's actually go and do that real quick. It's going to be pretty easy. I'm just going to do another case statement. And it'll look like this. It'll look very similar to this one. The only difference here is that select is going to be a multi-bit signal. Let me get rid of this. And so you'll notice before I had 1-bit signals. Here I'm going to have to put 2-bit signals because select is 2 bits. And because of that, there are now 4 cases. So I'll go ahead and do that. and that is my behavioral module. It's the same case statement as we used earlier, except the only difference is that here select is multi-bit. So in my case statement, I use multi-bit cases. So here there's 4 cases, 0, 0, 0, 1, 1, 0, 1, 1. And in each case, I just say, okay, I let either A or B or C or D go through. And that's it. That's the behavioral description. Both of these modules will do exactly the same thing. So if you were to have a black box of both these modules, you shouldn't be able to tell the difference. The internal gate logic might be different, because what I've done here is I've made multiple multiplexers, 3 to be precise, whereas here it might make it, instead of 3 separate multiplexers, it might make one big one with a bunch of logic, kind of a bunch of gates connected to each other. And other than that, other than the internals, they both functionally do the exact same thing. Okay, so any questions about that? Okay, so does anyone have any other general Verilog questions or system Verilog questions? Okay. Yeah, we can go over an FSM problem. It was the same, we did one example on Thursday, so you can also look at the video from Thursday and see what that one was looking like. So besides the FSM, we can't go over that if no one else has any questions, but does anyone else have any other suggestions for what they want to go over? Okay, so yeah, we can totally go over an FSM. Here's what I'll do. I am going to show a general outline for how you want it to look. And then we can maybe specify it to a particular FSM diagram if we want. But generally speaking, if we were to think about the schematic for an FSM, it consists of 3 things. So those things are going to be a state register, which basically tells you what the current state is. So you have your register, your schematic. And the next thing you have is the combinational logic leading into your register, which determines the next state. So that's called the next state logic. And then you typically also have output combination logic. So those are 3 steps. And so I'll go ahead and draw those up here. So I'm going to have some signals. And let's do names, state. Okay, so here's the first part, the state register. So whenever you want to make a register, which is the same thing as a flip-flop, if you want to make a flip-flop in System Verilog, you type always _ff to specify that it's a flip-flop. And then you say at, and then inside of these parentheses, you tell it what signals the flip-flop should react to. This is called the sensitivity list, because the flip-flop is sensitive to these signals changing. And so what I can type up in here is say pause edge clock. And I'll go ahead and add that as an input signal. So CLK. And so now what this is going to do is whenever you have a positive edge of the clock, the flip-flop is going to read what I have written inside this block and execute it. In terms of hardware, it's just behaving like a flip-flop. And so in Verilog, we say, okay, when we hit a positive edge of the clock, okay, well, if we want to reset, then something's going to happen. We're going to set the register, say, to all zeros. Otherwise, we're going to do something else. This. Otherwise, our state is going to move on to the next state. And so I'll go ahead and write that up here. So I'll do, let's do a 3-bit state register. And I'll make some internal signals. So I'll say logic 2 to 0, and I'll call this state, and then next state. So if we have reset on, that means that our state is going to go to, well, there's a bunch of ways we can do this. I'm going to say 3 bits of binary 0, and I'm going to change this later. So I'm just saying reset to state 0, 0, 0. So all of them are zeros. I could also write it like this. That means the same thing as if I wrote it like that, which is the same thing as if I wrote it like that. It doesn't matter how you write it. Otherwise, my state is going to be whatever the next state dictates. And that's going to come from the combinational logic. Yes.
It's like if the state is true, it goes to the future 0, 0. But
So, yeah, I'll read this kind of and say what it means. So if reset is on, so I'm going to have an internal signal called reset, or I'm going to have an external signal coming in called reset. And if reset is on, then the register, the values, and the contents of those registers are going to be written to all zeros. That's what this first line is saying. The second line is saying is that otherwise, if the reset's not on, then normally you have inputs to the registers, right? That come from your combinational logic. It's just going to read from those. And so this next state is going to be the output of the combinational logic. Okay, good question. All right. Now, before I continue, and before I continue on to the next state logic, I'm going to make some names for some states. So typically when we do it on our FSM diagram, we put state names that make sense to us, that correspond to whatever the states are. And then later we encode the states in binary. In System Verilog, or in Verilog, you can do either. You can do it with the encoded in binary, or you can do it with names, and you kind of encode it prior, and you can still use names. So this is with parameterization. So I can say parameter, and I'll say SR for the reset state. And because I have a 3-bit state, I'll call this 3 bits of binary 0, 0, 0. Okay, and then maybe, let's say I have a few other states. Parameter, I'll call this S1, and I'll say that's 3 bits of binary 0, 0, 1. Let's do that a few more times. 1, 0, 0. 1.
and then if you wanted to do like encoding, it would be like the same page.
Yep.
The syntax would be the same.
Syntax would be very, very similar. You just change this to 0, 1. This would be 1, 0, etc. Yep. Okay, so let's stick with this for the moment. And now, whenever we say SR, or S1, or S2 in our code, it's going to understand it as these binary sequences. And so we already have the state encodings done, we just don't have to think about it. And so instead of putting 3 bits of binary down here, I'm going to put SR. Because what happens when your reset goes off? You go back to state SR. So it's easier to think about if it's written that way. All right, so now what I'm going to do is I'm going to write some next state logic. And typically, instead of writing gate level stuff, because you need to go through all the truth tables, you would normally go through a case statement. So again, we're going to do another case statement. And what's the first thing I have to put for a case statement?
Always calm.
Yes, always calm. Always calm. And inside of that, I'm going to put a case statement. And I'll go ahead and do it based off of the current state. So in your next state logic, you typically have your case be the current state. And then inside of here, you write out all of those cases. So you could have the case where you're in state SR, where you're in state S1, S2, S3, and S4. Again, this makes our life way easier because instead of having to write 0, 0, 0, 0, 0, 1, 0, 1, 0, we can actually write the names of the states, and it's easier for us to understand. Okay, so now let's actually write out some logic for these. And it depends on how many transitions you have. And I'm just going to say, let's pretend there's only one transition from the reset state, and the transition goes to S1, and it's always taken. Here's how you would write that. Next state equals S1. So no matter what happens, if you're in state SR, your next state is going to be S1. Now for state S1, let's say there are two transitions. And I'll go ahead and edit my port list here. Say this is going to be A. Whoops. So we have an input A to our FSM. And let's say that this state actually depends on A. If A is on, then our next state, then let's say we transition to the next state after this, S2. So we'd say if A is on, then the next state is going to be equal to S2. Now otherwise, if A is not true, then let's say we have a transition that stays in S1. So a circle back to itself. Then we would say next state equals S1. And in general, this is how you're going to code up almost all the transitions, where the inside of this if statement, or maybe if you have an if else, is going to be just the thing that's on the arrow for the transition. Yes?
Like, if it was like a couple numbers, like if it was 5, 7, 9, and then would you put if, and then the numbers say it's commission?
There's a bunch of different ways you can do it, yeah. So you could do, in that case, so A would be a 4-bit signal, and you could, if you wanted to, one way to do it would be if A is equal to 5, or if A is equal to 7, or if A is equal to 9. So yeah, that's right. Kind of like for your guys' question where you had to do if it is 5 or 7 is 9. This would be one way to encode it. Yep, that's right. Or you could do it at the gate level, figure out what the gates are, but again, it doesn't really matter how you code it up. Okay. I mean, I could come up with more examples, but for now, you would fill up these with the rest of the transitions. So under SR should be all the transitions coming out of SR. Under S1 should be all the transition coming out of S1, et cetera, et cetera. And the last thing we would do is we would have the output logic. And this can also be in a case statement, but you can normally get away with it being an assign for this class because it's typically not a whole lot of trouble. Let's say that we wanted to assign the output Y to be on if we're in state S4, so the last state. Well, then what we would say is assign Y equal to, and we want it to be on if the current state is S4. If we also wanted it to be on during state S1, we could add that in here as well. Just make sure that you have your parentheses here, because the OR has precedence over the comparison equality, and it'll basically OR these two signals and then do the comparisons, and it'll be really weird. So make sure to put your parentheses, especially for this last one, at these states. Just as a quick question, from this code, do I have a more or a mealy FSM? And why?
Looks like a more one
Why do you think it'd be a more FSM?
because you don't have an output asserting on every input.
Yes. So remember that for a mealy, we have the output is dependent on the inputs as well. So that would mean that we would have maybe something like A and here. And so because of that, now Y is dependent on an input A as opposed to just whatever the current state is. Cool. All right, so I'll go ahead and zoom out a bit so that we can see the whole thing at once. And I'm just going to read over it real quick to make sure that I didn't make any silly mistakes. Okay, everything looks good. I'm just going to remind everyone, whenever you're dealing with a sequential block like this, you have to use the gets, the arrow signal for assignment. Whereas if you're in a combinational block, like always com, or if you're doing an assignment statement, you just use the regular assignment operator of an equal sign.
Could you use the get operator, or does it have to be assignment operator?
In which case?
You said so for if it's an always FF, you have to use the get operator, right? So,
Yeah.
but for an
So
always
like-
com,
uh-huh.
we have, is it like always an, we have to use the assignment operator, or could we use the get operator as well?
I'm pretty sure. I think it gets mad at you if you don't use the assignment operator. If you do gets, I'm pretty sure it'll be a compiler error. Does everyone know the difference between the two? So this is the gets operator. It's also called non-blocking assignment. I don't know if you've heard that terminology before, whereas this one's blocking assignment. And the main difference is as follows. Let's say you have within just some block. We don't know what the block is, but we have a begin followed by an end. And then inside it, we say something like as follows. A equals B. And then we have... Why is it capitalizing? Whatever. And then we say maybe B equals C. Now, for a moment, let's kind of think of this as C++ code.
Shift your screen.
Oh, am I?
Right now,
Oh, let me shift it, thank you. Is it?
at least to me, I'm not sure if it's turning out for you. Oh, really? Yeah, I'm not seeing the entire screen. Actually, no,
Okay, cool. So let's consider this code and let's think about it like C++ code for a moment. A is going to be assigned to B. So on this line, we have, say B was 7. That means that A is also going to be equal to 7. And then on this line, I'll do this backwards. C, go to A. Then C is also going to be assigned the value of A, which was 7. So in effect, there's kind of a time analysis here. This occurs first, and so by the time we get to the second line, A is already the value 7. If originally A was 4, it wouldn't matter, because here on this line, B gets assigned into A is 7, and then C receives the value 7. So this is sequential coding, whereas if you do this, it all happens simultaneously in parallel, like you're reading between registers. So if A was originally 4, on this line, A is going to read in 7 from B. But then here on this line, both of these are executed in parallel at the same time. C is going to be 4. C is going to get the value of 4 because that's what A was before this entire block executed. So in general, you use this for parallel operations when you have things happening at once, whereas for combinational stuff, you do it with equal signs, non-blocking, or blocking assignments. That's the main difference. So the equal sign you can think of as C++ code, whereas this happens in parallel. Okay, any questions? Okay, so I already went through an FSM example. I can fill these in if you guys want, but just let me know if you want me to fill in those extra states. Were there any other examples that anyone wanted me to go over in code or just in general? Okay. All right, so we have about 10 minutes left. So I could go over some conceptual questions. Specifically, I know a lot of students have trouble about skew, so we could go over skew if anyone wants to. If there are any other suggestions, feel free to make them. Go over skew. Okay. I'm probably not going to write it on the board because it's really hard to see with the markers. Okay, go for it. Yep. So, let me go ahead and pull up. I'm going to go ahead and share my screen here. Let's turn that on. Okay, cool. So I'll go ahead and draw an example of skew. So let's say we have the following diagram. We have one register, I'll call it register 1, and then we have it receiving a clock. And let's say that there is, say, some combinational logic that it goes through, and then this outputs to another register. And I'll call this register 2. And in a normal circuit, we would say, okay, these two clocks are received at exactly the same time by both registers, so they're synchronized. However, oftentimes what happens is there's a little bit of skew, which we can model or represent with a little buffer between the two clocks, like this. And so now, instead of this being clock, this is the delayed version of clock. And what we have, if we were to look at a timing diagram, is if we looked at the clock 1 and 2, 1 would look something like this, and 2 would receive that same clock, but shifted in time because it receives it later. So instead it might look something like this. And here the skew, denoted T-skew, is just the difference from here to here. So we would call that the skew time. Now, skew can go the other way around. It could be oriented such that 2 receives the signal first, and we can consider that later. But for the moment, let's just say that 1 receives the signal first. What would be the equation for the hold time in this particular scenario? And let's just ignore skew for a moment. What is the equation for hold time? And it's okay to be wrong. You can shout out answers.
T sub TCQ plus T contamination delay.
Yeah, so we have the contamination delay of being read out of the register. So this TCCQ, that's the time it takes from this clock hitting the register to the value inside the register being read out onto the wire. That's TCCQ, and that's the fastest time that that can happen. And then we have that plus TCD. Remember that the C stands for contamination, or the quickest. So TCD, that's the quickest path through this combinational logic here. Whatever that combinational logic is, it's the quickest path through it. And that symbol there, that's a combinational logic symbol. And now the question is, do we add or subtract the skew? And that just depends on what the orientation is. So I'll just tell you verbally, if it's skewed to the right like this, the skew is going to be added. Whereas if it was skewed to the left, it'll be subtracted. And that actually works for both equations. So if I was to write TC greater than TPCQ, so this is going to be, the clock time has to be longer than or equal to, or greater than or equal to, the longest time to be read out of the register, plus the longest delay through the entirety of the combinational logic, plus the amount of time that we need to sit there waiting at the entrance of this register for it to be read in. So there's that additional setup time. I'll call it T setup. I'll just say T set for T setup. And then we have the plus or minus the skew over here. In general, and we can talk about how to derive this if you guys are curious, because it is important to know how to get the plus or the minus from the diagram. If it's right biased, which is to say, again, that 1 receives the clock before 2, you're going to add these to both equations. And if it's left biased, i.e. register 2 receives the clock before register 1, you're going to subtract these terms instead of adding. And as a final point, when you add a term over here and when you add a term over here, we like to consider which one's the best case and worst case scenario. And it's always the opposite. So if it's the best case scenario for hold, it's going to be the worst case scenario for TC and vice versa. So if we're adding to TC, let's think about what that does. If we're adding to TC, that means that our clock time is going to be longer. So what's going to happen to our frequency if our period is longer? It's going to be lower. We're going to have a lower frequency. So let's say originally that my period was 150 picoseconds. And now I've just added a skew of 10 picoseconds. So my new period has to be 160. Well, if we were to check what this frequency is, it'd be 1 over 150 picoseconds. And that would come about to, say, let's call it 6.2 gigahertz. Whereas if I calculated the frequency for 160, that would be a little bit less because you're dividing by more. So it would be maybe something like 6.1 gigahertz. Now, we would prefer our circuit to operate faster, which means we want this. This is what we want. However, adding the skew here made it worse, lower frequency. So this is actually the worst case scenario for TC. And so what we actually have, according to this diagram, is when it's a right skewed bias, when the clock is skewed to the right, that means that our clock time is in its worst case scenario. Whereas the hold time we can analyze is going to be in the best case scenario. So let's check if we add skew here. We want the hold time to be smaller than the shortest delay through our circuit. Because if it's not smaller, that means that our signal is going to propagate all the way to the register and mess it up before the register has a chance to read in the value from the wire. Now, if we add skew here, and let's give ourselves an example, say in total before the skew, this was 15 picoseconds, and the hold time was 17. So not including skew, does this work? No, our hold time is violated because 17 picoseconds is not less than or equal to 15 picoseconds. But now let's add 5 picoseconds of skew, and let's see what happens. Well, if we add 5 picoseconds of right-handed skew, what that means is 17 picoseconds now is less than 20. So actually, this can only make the hold time constraint easier to meet. And so this is the best case for the hold time. So, to recap, if it's right skewed, like in this diagram, so 1 receives the clock first, that means that you're going to add the skew to both equations on the right-hand side, and that the hold time is in its best case scenario, and that the clock time is in its worst case scenario. Exactly the opposite happens if it's left bias skew. So left bias skew means that clock 2 receives the clock first. You subtract the skew from both equations. Your hold time is in its worst possible case, so that's worst case, but your clock time is in the best possible case. You can get these just by analyzing our equations again and saying, what happens if I subtract? So if I were to subtract 10 here instead of add 10, I would go down to 140 instead of up to 160. And 1 over 140 means a higher frequency than 1 over 150, so it's good for TC. And very similar if we subtract over here and say this was 12 picoseconds. Originally, if it was 12 and 15, it would work. But then if we subtract 5 picoseconds, now it's going to be 12 is not less than 10 picoseconds, and now it doesn't work. And so that would be the worst case for the hold. Okay, so I've gone over kind of the basics for it. I haven't described how to kind of maybe prove to yourself when this is plus or minus, besides just saying, hey, if it's right biased, it's plus, if it's left biased, it's minus. So do you guys want me to explain why? Because I can. It'll take me like 10, 15 minutes.
Isn't it based on the timing diagram?
It is, yeah, it's based on this timing diagram, that's right, yep. So if we were to like place the times here, say this was, let's just do it real quick. So the clock time here, TC, consists of these 4, in particular these three, and then skew added on top of that. So let's say we have TPCQ, that's this first one, followed by TPD, that's the second one, and then finally followed by the setup time. Let's actually do it like this. Okay, now let's go ahead and ask ourselves, does this work? Is this within the proper clock time? Well, if they were both synchronized, we started here at the first clock edge and ended before the second clock edge. So we're actually good if it was synchronized. And if it was not, and if it was in this orientation, it's not, you'll notice that we actually have a bunch of extra time here. Okay. So now let's see what happens if we add some skew on. So we add some skew on, and you'll notice that if the skew was a little bit longer, we actually have a worst case scenario. This is bad. This is not going to work. So again, like we mentioned before, we had a clock time, and we said, hey, this needs to be greater than or equal to all these. And then suddenly, if we add some clock skew, now this period isn't going to work anymore. We have to extend it further, because the clock skew actually goes further past it. So that's how we know that adding is the worst case scenario. Okay, so I've talked about Verilog coding and specifics for Verilog coding, and I've talked about skew and kind of a few things that'll help you remember how to do the skew on the test. Does anyone have any other questions for me? Okay. All right, so we're a little bit past, a few minutes past, that's fine. But your guys' exam is on Wednesday, so that means we have one more office hour before your exam. So if anyone wants to bring in specific questions, like you have a particular problem that you had for homework, or just like a similar problem that you want me to work on Tuesday, please bring them in. I'd be more than happy to work through them. Or if you have any conceptual questions, bring those in again. But other than that, I'll see you guys on Tuesday.
Thank you so much.
Thank you very much.